Welcome to our deep dive into the life cycle of building artificial intelligence systems. Today, we're exploring the complete journey from a rough concept to the final retirement of an intelligent tool. Developing these systems is highly repetitive and requires a flexible mindset. Organizations usually discover that combining strict, step-by-step project management with fast, flexible, agile methods works best. Before we get into the technical details, let us discuss why this matters to your career. As an auditor or technology professional, understanding this life cycle gives you a massive advantage. It allows you to confidently step into any corporate project, pinpoint exactly where data security might be slipping, and determine whether a proposed multi-million-dollar system is actually a sound investment or a disaster waiting to happen. Our first major phase is developing the use case. A use case is simply the specific business problem you want the technology to solve. It is a harsh reality that many corporate intelligent technology projects fail. People often get swept up in the hype and expect miracles. Research shows these failures almost always come down to people, processes, or data. Specifically, there are 5 common culprits. First, the team misunderstands the core problem they are trying to fix. Second, the data is messy, incomplete, or completely absent. Third, the tool being built does not actually address a real business need. Fourth, the company lacks the computer servers and technical foundation to keep the model running. And fifth, they try to use algorithms to solve a problem that is simply too complex or abstract for current technology. To avoid this, a solid project focuses heavily on the actual problem rather than the shiny new tools. Think of it like buying a heavy-duty commercial oven. You would not buy one unless you specifically plan to open a bakery. A good plan requires adequate time, an understanding of the technology's limits, and massive amounts of high-quality, cleanly organized information. Furthermore, success demands a tight partnership. The engineers must deeply understand the business context, and the business leaders must measure success based on actual financial returns, not just technical performance metrics. Once you have a solid plan, we enter the design phase. Unlike standard software where developers just write rigid rules, this phase is all about exploring the data to see if it holds the answers. The first step here is data ingestion. This means gathering isolated pieces of information from all over the company and pouring them into one massive central storage area, commonly called a data lake. Over time, engineers build automated pipelines to keep this lake constantly supplied with fresh information. Next comes feature selection. In statistics and basic machine learning, which use mathematical formulas like support vector machines or decision trees, humans have to manually pick the variables the computer should look at. We call these variables features. Imagine trying to predict the price of a used car. The features would be the age, the mileage, and the brand. If you pick too few features, you get a problem called underfitting. The system is too simple, it fails to see the real patterns, it cannot adapt to different broad situations, and it cannot explain the real drivers of the problem. Imagine guessing a car's price using only its color. You just do not have enough clues. On the flip side, if you pick too many features, you get overfitting. This is when the system essentially memorizes the exact examples it was shown, but completely fails when you show it a new, slightly different car. Having too many clues also causes the computing cost to skyrocket and makes it impossible to interpret how the system actually made its decision. Modern deep learning changes this. Deep learning is an advanced technique that extracts these clues automatically without human help. It powers things like facial recognition and voice assistance. Large language models take this further using a structure called a transformer. Instead of picking features manually, engineers make indirect design choices. They do this through tokenization, which is how a sentence is chopped up into smaller digital syllables, and embeddings, which is how the computer maps the mathematical relationships between those chopped up pieces. When auditing this phase, remember that simple, human-guided systems are much easier to inspect than these deep, automated systems, which require deep inspections of the original data lake. Moving on, we reach the development stage. For normal software, developers test things using fake, dummy information. but advanced intelligent systems require real, highly sensitive information to learn properly. Because real data is in play, strict security and privacy controls must be locked down even on the developer's personal laptops. Before the system can learn, the data goes through pre-processing. This is the deep cleaning phase. Engineers fill in blanks, remove duplicates, and normalize the formatting. For complex systems that read documents, this is a massive compliance checkpoint. You must verify that the company has legal permission to use the information. If a customer opted out, their records must be scrubbed. Sensitive financial or medical details must be aggressively removed to prevent the system from accidentally blurting out someone's private history later on. Once pristine, the data is split into at least 3 separate groups to prevent bias. The first is the training dataset. This is the largest chunk, making up roughly 60 to 80% of the pile, and it acts as the textbook the system studies. The second is the validation dataset. This takes up 10 to 20% and acts like a practice quiz to help engineers tweak the system's settings. Finally, the testing dataset takes the last 10 to 20%. This is strictly reserved for the final exam. Then comes the actual model training. The data is fed into the algorithms. Engineers adjust specialized control knobs called hyperparameters, such as batch sizes and attention heads, to guide the learning. This process can take anywhere from a few hours to several weeks and can cost millions of dollars in computing power. Because it consumes so much electricity, auditors must consider the environmental impact. The training is closely monitored to stop it early or randomly drop nodes if it starts memorizing the data too closely, and frequent saving is required just in case the servers crash. After training, we enter the evaluation stage. The system is graded using its performance on the validation data. We measure precision, which is how often the system is right when it claims something is true. We also measure recall, which is its ability to find all the correct answers hidden in a pile. These two are balanced together into a single grade called an F1 score. If the grades are bad, the engineers tweak the settings and try again. Once perfected, it takes the final exam using the untouched testing dataset. Crucially, teams must also test the system to ensure it does not produce toxic, biased, or harmful outputs, keeping meticulous records of these tests for future audits. Then comes deployment. This is where the complex math is wrapped in a clean, user-friendly software interface. The system is now live and performs inference. Inference simply means the system takes a brand new, unseen question from a user, processes it, and delivers an answer. Once live, the work does not stop. We move into monitoring and maintenance. Over time, you will encounter a major issue known as drift. Drift happens when the real world changes, but your system stays exactly the same. Imagine building an algorithm to recommend winter coats based on December shopping habits. When July rolls around, the real world has shifted, and the system's recommendations will suddenly be completely wrong. To catch this, a new field called observability has emerged. Observability acts like a continuous X-ray, constantly watching the system's health and helping engineers understand why it makes certain choices in real time. When performance drops, the system must be maintained by retraining it with fresh information. Eventually, every system reaches the decommission stage. Shutting down an advanced model is much harder than simply turning off a server. You must locate every single side project or derivative tool that was built using the core system. Also, because these giant models learn complex patterns, you cannot easily force them to cleanly forget specific pieces of data without completely rebuilding them from scratch. Let us recap the core takeaways from this session. Building an intelligent system is an endless loop of planning, designing, cleaning data, training, testing, and monitoring. Success hinges entirely on picking a practical business problem and feeding the system pristine, legally compliant information. As auditors, your focus must remain sharply on how data is handled during the deep cleaning phase, how the system is prevented from memorizing private details, and how the organization detects when the real world has drifted away from the model's training. That brings us to the end of our discussion on the system development lifecycle. To ensure you have completely mastered these frameworks, head over to RooCloud.com. All the important topics and concepts we covered today are heavily featured in the multiple choice questions on the platform. We highly recommend solving these chapter-wise questions to reinforce your learning before you move on to the next session. Thank you for joining, and keep up the great work.